Voilà, soyez le bienvenu. We continue the third part of our series, bar bending schedules. Let's begin with hooks. Okay. First of all, as you notice here on the right side of your screen is that what you're seeing is a column. This is a vertical structure member element. Inside the column, you find reinforcement bars. These long ones are known as longitudinal bars. Then you have these that hold these longitudinal bars in place. These are known as ties. You must not misunderstand stirrups and ties. Stirrups are found in beams, okay? They are there in order to resist the torsion effect. The torsion effect, when a beam is subjected to torsion effect, they assist in keeping the beam in position and also the bars in position. Whereas ties are found in columns, okay? That must not be misunderstood. So on this other part, you have the cross-section view of this column. Then you have this tie that is round the bars, this tie. Then finally, it has these two hooks there. These are the hooks we're talking about. This length of this hook must be put in consideration when preparing a bar bending schedule. Now, what are the functions of these hooks? The function of hooks in ties, to be specific, not stirrups, stirrups are found in beams and not columns, is to prevent seismic movements, prevent concrete from splitting outwards, okay? Prevent slippage of steel from concrete, to keep longitudinal bars in position when subjected to that compression effect, which might lead to the buckling of our column. We introduce what is known as hooks to our ties. So now, these hooks, how do we develop this length for hook length? Okay, we have what is known as develop anchorage or developmental length. We're talking about the length that is necessary in order to distribute evenly the stress inside the concrete, so as to ensure that our steel is firmly gripped inside the concrete. We need that developmental length. Now, that length required to ensure this grip in concrete is what we call developmental length. Now, as we move on, how do we deduce the cutting length for our hooks? The standard is that the length of the hook is 9D. D refers to the diameter of that specimen bar, the bar that you're dealing with. So diameter of bar, if our bar is T16 or Y16, you multiply 9 times 16 plus the total length here. Since you have two hooks there, it will be 9D plus 9D plus this particular length. Then you have the total length of your rebar. Okay, so hook length is given by 9D, 9 times diameter. That is how we deduce the length of our hook. Now, calculating the weight of our steel. What is the weight of the steel per meter? The formula for calculating weight of steel is very important. Remember, on our bar bending schedule, we must have weight stipulated per meter, then the total meters and total weight. Weight of the bar per meter is given by diameter squared over 162. The units are in kg meter. Okay, remember it's per meter. Diameter squared. In a case where, for example, we have our bars, which is 8 millimeter bar, it simply means we're applying the formula. It would be 8 squared over 162, which is equivalent to 0.39 kg per meter. Now, if, for example, since these bars are sold in 12 meter per unit, 12 meter one bar, then you're going to multiply your 0.39 kg per meter times 12 meters, which gives you 4.75 kg per bar of 8 millimeter bar. So when I'm going to buy in town, one bar which has a diameter of 18 millimeter, which is 12 meters, weighs 4.75 kg per bar. So this is the standard formula that a good engineer must understand when you're dealing with rebars. Voila. Now, let's talk about bends now. Not hooks, bends. The bend length is given as 10D to 16D. So there's a range when dealing with bend length from 10D to 16D. D refers to the diameter of the bar. The cutting length, therefore, is given by L, which is this middle length there, plus 12D plus 12D. That is now giving you the cutting length. You will tell the metal fabricators, you will indicate they will cut this particular distance for these bars. When bending them, we put them into consideration. So you have your bar in there like that. You have your bar in there like that. This bending length, you put it in consideration. This is your clear cover there. I mean, this is effective cover, not clear cover. Voila. We move on. Now, overlapping. Okay, we understand that when we're dealing with steel, which is not sufficient for the required length, we usually overlap it. We do not weld it. We only weld reinforcement bars with diameters of 36 millimeters and above. For diameters which are for steel bars, reinforcement bars which have a diameter below 36 millimeters, we overlap them. So for in concrete, for members or for the section in our concrete that is experiencing compressive forces, we consider the lap length as 40D, or 40 times the diameter of bar. So this simply means if this section of our concrete is subjected to compressive loads, then we are going to consider this distance from this part to this part as 40 times diameter. Diameter of this same bar, the same specimen we are dealing with in columns. Okay. Now, for a section that is in tension, for example, this bottom part which experiences high tension, you're going to consider this lap distance, overlapping distance, as 50 times D, 50 times the diameter of the bars. These are basics that we must understand. Now, overlapping reinforcement. For example, in a situation where you are connecting a neck column to the footing, okay, the neck column to the footing, of course, your reinforcement will have to overlap with these base of your basket reinforcement in your footing. So now, this distance here is called the lap length for neck column to footing. This distance is considered as a 16D. Okay, the lap length for neck column to footing is 16D. 16 times the diameter. Then you have your plain cement concrete bed at your base there. Voila. Now, crank bars. Let's talk about crank length. Crank length. For example, in a situation where you're connecting a beam to column, there is in a situation where your beam is susceptible to torsion effect, okay, and high shear forces, high shear effect. Therefore, you're going to introduce what are known as crank bars, okay? These crank bars are bent at an angle, and the formula for calculating this distance here, this length from this bend to this bend, this distance is known as crank length. The crank length is given by 0.42D. 0.42 times diameter of this same bar. This distance is given by 0.42 times the diameter of this particular bar. Therefore, the total length, therefore, will be given as this length, this total length will be equivalent to this distance here plus crank length, and crank length plus this particular distance here gives us the total length, okay, which is our cutting length. So how are we going to do it? These are significant details you must understand. So the distance from this end here up to where the bending of our crank length begins is given by L, this total distance, divided by 4. From this particular point to this point, it's L divided by 4. This distance from where the bending ends to where the bending ends here is given by L over 2. So you have got this distance, L over 4, plus crank length, plus L over 2, plus crank length, plus L over 4 to give us the total cutting length. Voila, I hope you understand that. Okay, so these, I repeat, these are the basics that you must have at the fingertips in producing a bar bending schedule. Now that we have these distances, let us go now the practical steps in making a bar bending schedule. See you.